Hello everyone. This is a video where I'll be discussing questions from JEE Advanced levels. You can see the name of the video as JEE Advanced, solving JEE Advanced questions for fun because I love solving questions. I love solving numericals, and that's what I'm gonna do in this video and in this lecture series, where we'll be solving JEE Advanced questions, and yeah, we'll do them for fun. Okay, we'll do them in a fun way, and we will not take much stress. Alright, yeah, let's do it. Okay, this is the first question. A square metal loop of side 10 centimeter resistance 1 ohm is moved with a constant velocity V naught. Okay, and, and this is the loop here, and you can see the resistances are here, right? And what is the question? Magnetic field lines are perpendicular to the plane of the loop, directed into the paper. The loop is connected to the network of resistance each of resistance 3 ohm, right? And the resistance of the resistance of the lead wires is negligible. The speed of the loop so as to have a steady current of 1 milliampere is. So the V speed of the loop is asked. Okay, and we know effective. Okay, first of all we have to find the effective resistance here. Can you find the effective resistance? Let's try to find effective resistance first of the circuit. Then we will move forward. Okay. Find the effective resistance of this. Yeah, done. Square metal of side, what is it? Square metal wire loop of side 10 centimeter. This is the 10 centimeter wire loop. And resistance 1 ohm is moved with constant velocity V naught in uniform magnetic field. This and magnetic field lines are perpendicular. Okay, the loop is connected to this. So this is the loop, and if you can see, it's a Western bridge. Okay, so the R equivalent is 3 ohm, isn't it? Because this is the 3 ohm will be disconnected. So this 3 will give me 6. This 3 will give me 6, and 6 will give me 3. And there is another 1 ohm, that is the resistance of the metal wire loop. So 3 plus 1, that is 4. So R is equal to 4 ohm, right? So magnetic field, that is in this here is wave of meters, that is 2 Tesla. Simple, 2 Tesla. Alright. So the resistance of the lead wires is negligible. The speed of the loop so as to have a steady current of this. So the steady current is given 1 milliampere, that is 10 to the minus 3 ampere. Okay, so the speed of the loop is asked. Okay, whenever the wire is inside a magnetic field. Okay, whenever the wire is inside a magnetic field, what is the potential difference? What is the potential? If you remember, the EMF induced will be BVL. Why the EMF is there? Because the wire is moving out of the magnetic field. That's why there will be a change in magnetic flux through the loop. Okay, because now suppose the this one here, right? So there are suppose 10 magnetic field lines going into the loop. Now it is moving away from it. Now it's here. So the magnetic field lines have decreased. So there is a change in flux. Because of change in flux, del phi by del t, there is EMF. Okay, because of change in flux, there is EMF, and EMF is equal to BVL for a moving loop. Okay, so our EMF is equal to BVL, and our current is there 10 to the minus 3 ampere. So resistance is there also. So we need to find only velocity. Okay, so I will write the equation. I is equal to E by R, right? EMF by resistance. So BVL by R. Your V is the velocity here, which is a V naught. It's given in the question V naught. So V naught will be IR by BL. Okay, just put all the values 10 to the minus 3. This is your 4 divided by B is how much? 2. B is a 2 into length. Length is how much given in this question? Length is given as 10 centimeters. So 10 into 10 to the minus 2, there is 10 to the minus 1. So this is 10 to the minus 2, 2 into 10 to the minus 2 meter per second. That is 0.02 meter per second. Alright. So this is the answer. 0.02 meter can be written as 2 centimeter per second. Okay. I hope you understood. I won't go that fast that you won't be able to understand. There'll be no point of this video. I'll go like with a normal pace. So the answer is 2 centimeter per second. Okay, first you had to just calculate the resistance, net resistance. That was the main thing. Okay, all right. Okay, let's move to the next video. Next question. This is the question. I hope you can see the letters. If you can't, then let me know. A conducting square loop of side L. Okay, and resistance R moves in its plane with a uniform velocity v perpendicular to one of its sides. Magnetic induction B concerning time and space pointing perpendicular to and into the plane the loop exists everywhere. The current induced in the loop. Okay. Hmm. Current induced in the loop will be what? So this is the question. So you please first try and let me know what is the answer. After that we'll do. These are JEE Advanced questions. These are old. We'll slowly move into the new ones. Okay. It's very old. 1989. Wow. Now questions are a lot tougher than 1989, but we'll slowly move into the modern era, whatever you will call it. Okay. Okay. Conducting loop of side L resistor moves in its plane with uniform velocity v perpendicular to one of its sides. Magnetic B induction B is there, pointing perpendicular to and into the plane of paper. Plane of the loop exists everywhere. Okay. The current induced in the loop. So that is the question. So see, the thing here is there is this magnetic field which is constant in time and space, and the loop is actually inside the magnetic field. And if you can see, the move it's written moves in its plane, okay, and it does not go out of the magnetic field, isn't it? And the magnetic field perpendicular to and into the plane of the loop exists everywhere. The magnetic field exists everywhere and it is constant, and the loop you can see is not going anywhere outside of the magnetic field region. So there is no change in magnetic flux because the magnetic field loop is not going anywhere. So magnetic flux, there is no change in magnetic flux. That means del phi by del t is zero. Flux is constant. So del phi by del t is zero means EMF is zero. EMF is zero means current is equal to E by R. That is zero. Okay, very easy. So the answer will be zero. Okay, yeah. I hope you understood. These are easy pickings. We'll slowly move into the advanced question. Okay. Yeah. Okay. Let's move to the next question. Thin circular area ring of area A is held perpendicular to a uniform magnetic field of induction B. A small cut is made in the ring and a galvanometer is connected across the ends such that the resistance of the circuit is R. When the ring is suddenly squeezed to zero area, the charge flowing through the galvanometer is. Again, it's not a tough question. It's the same type of question. Again, this is from JEE Advanced 1995. Okay, thin circular ring of area A is held perpendicular to a uniform magnetic field. Suppose this. Okay. B. Small cut is made in the ring. Suppose the small cut is there in the ring. Okay. Suppose this is the cut part. Okay. Galvanometer is connected across its ends. That means it's something like this. Okay. Galvanometer is there. Yeah. Such that the total resistance of the circuit is R. Total resistance of the circuit is now R. When the ring is suddenly squeezed to zero area. Now the ring is suddenly squeezed to zero area. So the area of the ring is changing. Okay. Area of the ring is changing. So these things matter nothing. This galvanometer, this all. So the charge flowing in the galvanometer. Okay. So the charge flowing, we know the formula of a charge is equal to flux by resistance, isn't it? Change in flux by resistance. So first, what was the flux in the beginning? Flux in the beginning minus flux in the final, or flux final in the beginning. So first flux was this is B, this is A. So B into A. and cos theta theta is 0 degree because this area vector and magnetic field are the same angle. Phi 1. Now what is the final? This suppose I take it as final your final flux. So it is squeezed to zero area. That means area is zero. If area is zero, flux is zero. Isn't it? Flux is B into A, so zero. So 0 by R. So answer is B A by R. Okay, very easy again. Option will be B A by R. That is option B. Another easy picking, you can say. Okay, yeah, big questions, but doesn't justify like any toughness. Okay, let's move to the next question. Thin semicircular conducting ring. Okay, of radius r is falling with its plane vertical in horizontal magnetic induction B. Okay, this please let me know if you can see it properly or not. Otherwise, I will change the resolution in the next video. Okay, so this is the magnetic field is into the plane, and this is a semicircular conducting ring of radius r falling with its plane vertical in horizontal magnetic induction B. At the position M and Q, what is the position M and Q? Whatever the position is, speed of the ring is V. Okay, that means this ring is going down in velocity V. Potential difference developed across the ring. Okay. So this is the ring. So M and Q. I hope so. This is the M and Q. So potential difference, that means Vm minus Vq is what we are asked in this question. Developed across the ring. Okay. Again, if you see, uh, okay. So we can say first actually the ring. Okay. I think the ring would have been semicircular conducting of radius r. Okay. This is the radius r. Suppose this one. So the area was pi r square by 2. Correct. Now falling with this plane vertical, this point, the potential difference developed across the. Okay. So what exactly is changing? Can you say what exactly is changing here? Hmm, What? Here the magnetic field is constant, so the area is changing. Okay, the area is what changing here, and okay, displayed vertical in horizontal magnetic induction B. Right. Magnetic field is constant, uniform magnetic field. So the area is something that is changing, and if we see, okay, so pi r square by 2. If the area is changing, then d, okay, flux will be what, minus d phi by dt, correct? Minus d phi by dt, which is equal to minus d by dt of b into a, right? Uh, so minus d by dt, b is constant, so it comes out minus d by dt of area. Area is your pi r square by 2. Okay, pi r square by 2. So minus b pi by 2 2r dr by dt. That's the EMF, right? Minus b pi by 2. Again, I will write minus b pi by 2 into 2r dr by dt, correct? Yeah, 2 cancelled out. So dr by dt is what? Dr by dt is the rate of distance is velocity. So minus b pi r v. So this should be the answer. Okay. Is it there in the options? Minus b pi r v, and q is, yeah, b pi r v. Will what I will consider. Is it correct or we are doing something wrong? Yeah, that's correct. All right. Next question. A small square of loop side L. Side L is placed inside a large square loop of wide wire of side L. Capital L. The loops are coplanar and their centers coincide. A small square loop, small square loop inside a large square loop. This is the small one, this is the large one. This is length is L, this length is capital L. The loops are coplanar and their centers coincide. Okay. Mutual inductance of the system is proportional. Okay, mutual inductance. Okay. So first of all, if we see magnetic field, okay, magnetic field produced by a current in a large wire. So large wire will be what? V is equal to mu naught I. Something, but not to R exactly, but we can say proportional to I by R, correct? I by R, or here L for the larger one. This is B large, proportional to I by L. Okay, we can say B is equal to Ki by L, suppose. Right. So magnetic flux. So this is the magnetic field with the larger loop, which will act on it. So the magnetic flux with the smaller loop will be magnetic field with the bigger loop into area of the smaller loop. So this is the trick. Okay, not the trick. This is the concept. So B big is what? Ki by L, capital L. A small is what? What is the area of the smaller square? L square, small L square. So we're getting B is, so flux is equal to, why are we trying to calculate flux? Because we need mutual inductance. Okay, so mutual inductance, we know direct formula is mutual inductance phi by I, correct? Isn't it? Phi by I, correct? So phi by I is how much? This just divide I here. So K L square by, okay. So is proportional to, so K is constant. We need only proportionality. So proportional to L square by. Very easy question. Again, nothing much is there. Just basic concepts. Yeah. Go to the next question. Please read the question. Uniform but time varying magnetic field. Okay, this is a time varying magnetic field. Okay, and BT, circular region directed into the plane of the magnitude of the induced electric field at the point P. Okay, at a distance r from the center of the circular region. Let's do it. We'll solve it first, then I will do easy questions. Okay, first of all, see, this is again a magnetic field, time varying magnetic field. Time varying magnetic field means, okay, if you remember, there is this Maxwell equation that is used for time varying magnetic field. That is what? E dot dl, okay, is equal to minus del v by del t. Sorry, minus del phi by del t. Okay, this is your EMF, right? This is your EMF. EMF is equal to minus del phi. This is actually Faraday's law of electromagnetic induction, and EMF can be written as E dot dl is equal to minus del phi v by del t. And here the magnetic field is changing with respect to time, but the area is constant. So area we will take out. So pi minus pi, and what is the radius? Radius is in it. So pi is square del b by del t. Okay, and this is E dot dl. Okay, E dot dl, electric field dot length. Okay, length. And what is the length of this circle? 2 pi r. So E into 2 pi a. Okay, 2 pi r, suppose. Okay, 2 pi r. Why 2 pi r? This actually, this loop is up to the distance p. Okay, up to the point p. This EMF is up to the point P, and this area is of the area in which the magnetic field is there. Magnetic field is there only for the region of this. Okay, which you might ask me why we didn't take this as pi r square. No, pi a square, because magnetic field is up to area radius a, but we have to find the electric field up to point P, that is of which is making a Gaussian surface of radius r. Okay, so that's the thing. So pi got cancelled out. So E is equal to minus a square by 2r del b by del t. Okay, so the option electric field point P and distance from the center of the region. Okay, E is inversely proportional to r here. Okay, decreases as 1 by r. Okay, option B will be the correct answer. Very good question again. It's a fantastic question. E is proportional to 1 by r. Okay, I hope people do it. Okay, next question. Try. You first try the question. Metallic square of ABCD is moving in its own plane with velocity v in a uniform magnetic field perpendicular to its plane. Okay, an electric field is induced. Metallic square loop again moving in its own plane with velocity v in a uniform magnetic. Electric field is induced. AD but not in BC, BC but not in AD. So yeah, you first drew it, then only I will do. Hmm. See, so here if you see, conductor is moving in this direction. Right? Velocity is in this direction. So the one, okay, the trick in this type of questions is the one that is perpendicular to the velocity, because the loop is already perpendicular to the magnetic field. So the one that are perpendicular to the velocity, that is AD and BC, will have EMF move induced in them. Okay, AB and DC will not have EMF induced in them. AD and BC will be the answer. So both AD and BC will be the answer. Alright. So electric field will be induced in what EMF will be induced in AD and BC. Hence EMF will be there. Electric field will be there because EMF is equal to minus. So EMF is equal to E dot dl, right? Minus also. Yeah. So this is the answer. Alright. Next question. Two circular coils can be arranged in any one of the three situations as shown in the figure. The mutual inductance will be maximum where? So whether it will be maximum everywhere or same somewhere, just tell me. Tell me. So this is A, B, C. Suppose 1, 2, 3. So which is maximum? Mutual inductance M. Okay. E is equal to minus M di by dt, or E M is equal to phi by I. Anything you can think of? See, it's a very simple question. You can also guess it from like the picturization also. See these two loops here. Suppose two coils are there. Na? So suppose mutual inductance. That means because of one changing flux through one, there will be flux change in other. So suppose magnetic fields are changing with this loop. You see, they're also changing with the other one, right? But here the case is you can see if a magnetic field is changing with this one, they're not passing through the other one. Okay. Or also here, if the magnetic field lines are going through this one, they're not passing through the. This is not the correct way of passing. So the option I will be correct because here the maximum magnetic field lines are passing through the other one, so maximum mutual induction will be there. Okay, because M is equal to phi by I, so flux should be maximum also. So then only your mutual inductance will be maximum. So option A will be the correct answer. This is the question number 13. Okay, easy questions. We haven't gone to advanced yet. Okay, question number 16. Try. This is for alternating current. When an AC source of EMF is given, Okay. A source of EMF is connected across the circuit. The phase difference between EMF E and current in the circuit is observed to be pi by 4. The phase difference is pi by 4. Okay. As shown in the figure, the circuit consists of possibly only of RC or RL or LC in series. We don't know. Find the relationship between the two elements. Okay, very good question. So flux is equal to phase difference. Okay, phi is equal to phase difference is pi by 4. Okay, do you know in any kind of circuit, okay, RC or RL or LC circuit, there is this tan phi. Okay, there is tan phi is there. So here, first of all, here we have to see which one is leading which one. See here, if you go back, you don't even have to go back. See here, current is here, EMF is here. That means current is leading EMF. Current is leading EMF here. All right. For time, current is leading EMF. So when I leads EMF, that means there is a capacitor in the circuit. Correct. When I leads EMF, there is a capacitor in the circuit, and the other one will be resistor. So this will be RC circuit. Okay. So this is an RC circuit. All right. So in an RC circuit, what happens? So okay, first of all, what is the formula for this phase difference? See, tan phi, if you remember, tan phi is equal to XC minus XL by R. This is the formula. Okay. So tan pi by 4 is what? 1 is equal to XC minus XL. Okay, first of all, there is no XL here. There is no, we just concluded this is an RC circuit. So XL is equal to 0. So XC by R. So here R is equal to XC, correct? So the resistance is equal to capacitive reactance because there is no inductor. Okay, so R is equal to XC. What is XC? XC is equal to 1 by omega C. Correct. X is equal to 1 by omega C. So what is the question now? Let's go to the question. Find the relationship between two elements. Okay, R and C. We just have to find the relation. So just put everything, put all the values. You just have to use the experience a bit, guess a bit. R is equal to 1 by omega C, and omega is how much? Sine omega t. Sine omega is 100. So omega is 100. That means R into C must be 1 by 100. Yeah. So just check which R into C is 1 by 100. Okay, first one, kilo, 10 to the power 3 into 10 to the power minus 6. This is 10 to the power minus 6. This is not the answer. This is 10 to the power 3. Okay, sorry, this is 10 to the power, okay, 10 to the power minus 5, sorry. So this is 1 by 100. Yeah, this is the answer. Option A is the answer. My bad. 10 microfarad means 10 into 10 to the minus 6, that 10 to the minus 5. So 10 to the 3 into 10 to the minus 5 is 1 by 100. So option A is the correct answer. So we got it. Okay. Again, a very good question. Again, a very good question. Next. Small bar magnet is being slowly inserted with constant velocity with a solenoid as shown in the figure. Which graph base represents the relationship between EMF induced with time? Do it. There is a small bar magnet which is being slowly inserted with constant velocity inside a solenoid. Which graph represents the relationship between EMF induced with time? EMF. We know EMF is what? EMF is minus d phi by dt. Alright. EMF induced with time. Okay. So first of all, mm, EMF will see. First of all, when the solenoid is moving towards the coil, the flux will increase through the coil, right? Flux will increase. Flux will increase. That means d phi by dt will increase. If d phi by dt increases, then the EMF will what? EMF is negative. Right? So EMF is negative. So EMF will be negative when flux will be increasing. EMF will be negative. So that kind of gives me the option C, isn't it? Straight away. Okay, let's check a bit more. Suppose we move the solenoid. Okay, suppose uh, and now what happens is after it moves completely towards the coil, okay, like okay, and moves inside the solenoid. Suppose the sorry, this is a bar magnet. I'm saying it's solenoid. The bar magnet goes inside the solenoid. What happens is the increase in flux slows down. Okay, after a time it will slow down. So flux slow down. That means change in flux will decrease. So EMF will become positive, right? This is decreasing. Flux decreasing means this becomes the derivative becomes negative. Negative negative gives me positive. So C, option C is the correct answer. It's a brilliant question again. Again a very good question. Okay, yeah. Next question, question number 19. Try. Figure shows certain wire segments joined together form a coplanar loop. The loop is placed in a perpendicular magnetic field in the direction going to the plane of the figure. The magnitude of the field increases with time. I want to it to segments. Then what? This is again very good question. Please tell me what. See, there are two currents here. Uh, Current I1 and I2. A loop is placed in front of the magnitude of the field increases with time. I1 and I2 are the currents, the segments AB. Okay, suppose this I1 is here. Okay, I1 is here and CD I2 is here. Alright, then okay, we have to see. First of all, the thing is, same current will flow throughout the circuit, throughout the whole loop, same current. But we have to see the direction, right? So as B is increased, suppose you increase the magnetic field. As B is increased, current will flow in the circuit from A to B, right? Why? Why from A to B? Why from A to B? Hmm. Okay. In the outer circuit, this is the same current, right? So it will go like this, and it will move from what D to C. See, this will go like this, going like this. The same current, isn't it? So D to C. But why here it is moving from A to B? See, the magnetic flux is into the plane of paper. So the magnetic flux is increase like the meaning of it. Okay, magnetic flux is into the plane of paper. Meaning of it is something like a south pole. Okay, sorry, north pole is going into it. Okay, okay. No, 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 sorry. Sorry. Magnetic field is going into the plane of paper. Alright. So, so the magnetic field is increasing. Okay, magnetic field is increasing. So the current will be in such a way. Okay, the current will be in such a way so that it will oppose the magnetic flux increasing through the loop. That's why if you see the final current is something like this. See I2. See, it's something like this, which will create what? North pole. Right. So the I2 direction is this, and it originates from I1, which is this. Okay, it goes like this to make it a north pole, which would oppose the current that is coming in, the loop that is coming in, magnetic field. So I1 is in the direction of AB, I2 is in the direction of DC. Okay, I hope you understood. Okay, again a very good question. Yeah. Okay, next. An AC voltage source of variable angular frequency omega and fixed amplitude V naught is connected in series with a capacitor and an electric ball of resistance R when W is increased, omega is increased. AC voltage source. AC voltage source, variable resistance, sorry, variable angular frequency fixed amplitude V naught connected in series with a capacitor and an electric ball of resistance R. Okay, this is a bulb. Resistance R, inductance 0. Okay. When omega is increased, the bulb grows dimmer, the bulb glows brighter, the total impedance of the circuit is unchanged. Total impedance of the circuit. Okay, first try this question. First of all, tell me the impedance of the circuit. This is a RC circuit, so impedance Z is equal to r square plus xc square whole root over, correct? Okay, xc is a 1 by omega c, so 1 r square plus 1 by omega square c square whole root over, correct? So as omega is increased in the question, as omega is increased, so as omega increases, what will happen? Z will decrease, right? Z will decrease, yeah. So when omega is increasing, Z is decreasing. Okay. Your current in the circuit will be what? Current is your EMF by total resistance, that is Z. So Z is decreasing. That means current will increase. Yeah. So the current will through the bulb will increase. Current through the bulb will increase means the bulb will grow brighter, glow brighter. Okay. Very good question again. Brighter. Got it? Omega increasing, that means Z will decrease, and we know current is equal to voltage by resistance, which is Z here. Z is decreasing, so current will increase. So the current to the ball will increase because it's a series connection. Okay, series connection, that means current, all the current will go through this, to the bulb also, to the capacitor also. So the bulb current increases through the bulb. That means the bulb will grow brighter, glow again. Sorry, glow brighter. All right. Yeah. Okay. So these were the questions we did today, and yeah, we'll solve more questions tomorrow. Right. I hope you understood. Any doubt you have, you may ask me in the comments. Okay. Yeah. Okay. Thank you very much.